Hello, everybody. This is Georgia, and today we're going to talk about the normal distribution, a very, very, very important chapter. I cannot emphasize this enough, so please pay attention. Read your textbook as well as listen to this lecture and go over your PowerPoint as well. I would highly recommend that you also practice as many Z problems as possible on your own and make sure you also do your homework, okay? It's going to prepare you well for the upcoming midterm. So what are our objectives for today? Number one, you need to understand why the normal distribution is important. We pretty much use it everywhere in statistics. To understand what are the three important properties of the normal distribution, and also you're going to learn how to calculate z-scores. All right, so the normal curve, this is it. This is a perfect normal curve, okay? Also known as the bell curve or baby-faced Nelson. The three characteristics of a normal curve, I would like you to memorize those. Number one, it is symmetrical. And what does it mean to be symmetrical? That means that this side here is equal to this side. The mean, second characteristic, the mean, median, and mode, they're all equal in value, so they all fall on top of each other, as you can see, one line here only. And the third characteristic is that the tails of the normal curve are always asymptotic. Asymptotic simply means that they're not touching the x-axis. A quick note here, um, this is both our skewed distribution. This is a negatively skewed distribution. This is a positive skewed distribution. What I want you to pay attention here is where the mean is. As you can see, wherever the tail goes, the long tail goes, that's where the mean goes. And can you figure out why? Because when we calculate the mean, right, we include every single score. So if we have an outlier, in this particular case, probably we have an outlier on the negative side, that means it's going to pull the mean this way. And in this particular case, probably we have an outlier on the positive side and it's pulling the mean to the right, okay? So just know how everything falls. As you can see, the median in this particular case is going to be to the right of the mean. That means that the median is always going to have a greater value. And also your book has a formula if that helps you out, figure out if the distribution is skewed or not. If you take the mean and you subtract the median from it, in this particular case, right, you're going to end up probably with a negative score, so negative skew. And in this particular case, the mean is greater than the median, so you're going to end up with a positive score if you subtract the median from the mean. So you have a positive skew. Now, why are the tails asymptotic? Again, asymptotic means that they're not touching the x-axis. The reason is because there's always going to be a possibility that someone's going to get a very extreme score. If the tail was to touch the x-axis, that means there's no probability of anybody getting this extreme scores, which is not possible, right? There's always the probability of somebody getting an extreme score. And again, this is the normal distribution, and anything on the tails, that means this is an extreme score. Average would be what the majority is, and that is the hump of the distribution right here. And anything on the tails, and as you can see, the tails are getting skinnier and skinnier and skinnier as they go towards the left and towards the right. Those are usually the extreme scores. Try to imagine in a class environment, right? You're having a test. Not the entire class will fail the test, as well not the entire class will get 100%. Probably there are going to be one or two people failing the test, scoring extremely low, right? And there's going to be a few people that they're going to score extremely high. Everybody else, they're going to be from the C range to the B range to the B minus, okay? So these, the tails always represent extreme scores, and that's why they're skinnier and the average is always a lot greater. Now, where do we see normal distribution? Okay, what variables represented by the normal distribution? Pretty much everything. Try to think of weight, right? Weight is normally distributed. Simply why? Because there's not too many skinny, very skinny people, and there's not too many obese people, although, obesity is an epidemic right now, so we definitely have more than we used to. Nevertheless, you would say that the majority of people, they're somewhere in the average weight range, right? GRE scores, SAT scores, right? Not everybody scores really high, and there are always going to be some people failing. Height is also normally distributed. Um, a few people are going to be extremely short, a few people are going to be extremely tall, and everybody else is going to be somewhere in the middle. Cholesterol levels, right? So pretty much everything we that you can think of, for the most part, is normally distributed. Now, why do we like the normal distribution in statistics? Well, I mean, I will have to say that not everything is perfectly normally distributed. It might have a little bit skew here and there due to an outlier. But in statistics, we do like normal distributions because simply we are able to identify what proportion of people falls under a particular area. So if we're able to locate the area underneath the curve of a particular individual, we can see what proportion of people will fall under that area. Because statisticians were able to calculate the area underneath the curve, so this would be like 100% of your entire distribution, and by knowing the exact location of someone's scores underneath the curve, we can identify their percentile. The standard deviation. We learned about how to calculate the standard deviation a few chapters back, right? So from now on, we're going to actually use the standard deviation quite a lot. So the standard deviation actually tells us quite a few things about the distribution. First of all, it determines how tall or how flat the bell curve is going to be, right? So when we have a very small standard deviation, apparently, right, the height is going to be greater because that means the majority of scores were very close together. Because again, the standard deviation tells you how far away an individual score is from the mean. So by having a very large standard deviation, that means that the scores are pretty spread apart. So your distribution is going to look pretty flat and wide, okay? Now we're going to use the standard deviation to calculate what we're going to call them the z-scores. So once again, if we design here a normal distribution, okay, and let's just say this can represent anything that you want. Let's just say these are the numbers of a test, or it can be cholesterol levels, whatever. So you have the average being 100, right? 110, 120, 130, and then anything below the mean in this side. So we can actually start measuring things in the form of standard deviation. So the mean is going to become a 0, and then 110 is going to be one. Let's just say that the standard deviation in this particular case is 10. So 110 is going to be one standard deviation to the positive side. 120 is going to be two standard deviations away from the mean. 130 is going to be three standard deviations away from the mean on the positive side. Likewise, we can do the same on the negative side, right? So 90, which is one standard deviation away from the mean, so it's going to be a -1. 80 is two standard deviations away from the mean, so that's going to be -2 standard deviations, right? And so on and so forth. And you're going to see where I'm heading with that. Now, this is a symbol that I would like you to know. So in statistics, anything with Greek letters, it's going to represent populations. Anything with Latin letters, or the letters that you know as English letters, is going to be for samples. So this is a Greek lowercase sigma, okay? Not the capital sigma, that is the summation symbol. The lowercase sigma, that is going to represent the standard deviation. You most likely going to see it as an SD. And if you see a plain S symbol, that is standard deviation as well, but that is going to be for a sample. So sigma, lowercase sigma, is going to be for a population. Now, this is where the standard deviation comes in handy, okay? By knowing how many standard deviations you are away from the mean, you can actually figure out the exact proportion of scores that fall underneath that area of the curve. So statisticians were able to calculate that. So we know, okay, and that's actually called the empirical rule, by the way, that from 0 to 1 standard deviation away from the mean represents 34.13% of scores. So if you, let's say this was an exam, right, and you scored 110, depending, let's say like 140 was a high score, so you would be 34% higher than the average, okay? Two scores, two standard deviations away from the mean, so from 1 to 2 would be 13.59%, right? So if we were to calculate from 0 to 2 would be 34 plus 13, okay? And as you can see, the percentages get a lot smaller as you're getting from the tail. Now, because the curve is symmetrical, if you remember from the very beginning of the lecture, that means whatever's on the right percentages, it's going to be also on your left side, right? So 1 standard deviation to the positive side, 13.13, 34.13%. 1 standard deviation to the negative side is going to be also the same amount since it is perfectly symmetrical. Only this side is going to be a negative sign here. Here is going to be the positive side. Now, once again, this is the normal distribution, and everything underneath this curve represents 100% of your total scores. And the majority of your scores, right, almost 100%, not 100%, it's actually 99.7% of your scores gonna fit between -3 and 3 standard deviations, okay? So every single time that we're having a normal distribution, the majority of your score is going to fall between -3 and +3 standard deviations. Anything beyond that is going to be an extremely, extremely rare score. Now, this is the empirical rule that I mentioned before. So the empirical rule is very useful if you want to memorize and actually can, play it smart by memorizing these numbers right here, 68, 95, 99.7. So what that represents, so 68 would be right here between -1 and +1 standard deviations away from the mean. You just add those two, and it's just much easier. Between 2 standard deviations to the positive side and 2 standard deviations to the negative side, this area right here underneath the curve represents 95% of the distribution. And between 3 standard deviations on the negative and the positive side, so from here all the way to here, that's going to be 99.7% of the scores will fall underneath ±3 standard deviations away from the mean. Now, z-scores, and this is something that you're gonna actually gonna use a lot. So a z-score is a standardized score, and we're going to talk about what is so special about z-scores, and it's also is not going to be explained inside your book. But first of all, let's go over the formula. So you're having z-score equals to an x value, right? So that can be any number, okay, that is being given to you, minus the mu, remember this is the population mean, over lowercase sigma, which is the population standard deviation. Now, the z-score, by knowing the z-score of any problem, you will be able to identify the exact location underneath the normal curve, okay? And a very basic thing that you need to know is that a z-score that is equal to 0, that means you're falling right on top of the mean. A z-score of 1, that means that you're 1 standard deviation away from the mean. Likewise, a z-score of -1, that means that you're 1 standard deviation below the mean, okay? So it very much relates to the standard deviation, but it's something that we calculate using standard deviation and using the population. Now, why bother to calculate the z-score? Once again, this is not inside your book. Well, if you think about it, depending where you practice science, if you're in Europe or if you're in America, we a lot of times use different measures. For example, weight is measured in kilograms. In Europe, here in America, you use pounds. Or you can use metric units, or you can use inches. Once you convert something into a z-score, you standardize it. So units no longer play a role, so you're actually able to compare. Also, by figuring out the z-score, you're able to determine the proportion of people in the population who have that particular z-score above or below another given z-score. So this is probably the most common reason why we use the z-scores for. So how do we calculate a z-score? Let's take a word problem here. So we have the average height in a given sample is 60 inches, so that's going to be my mu, right? And my standard deviation is 5 inches. If we pick an individual who is 50 inches tall, what is their z-score for height? Okay, so now the 50 inches here is going to be my x value, if you remember the formula. So right here we got the formula. We're going to solve. We're going to try to figure out the z-score to see how a person who is 50 inches tall fares comparing to the average, which is 60 inches tall. So if we plug this in, right, would be 50 minus 60 over 5, which is the standard deviation. And pretty much you're going to get a -2. That means a z-score of a -2. Now, on the very back of your book, Appendix A, you're going to find something that's called a z-table. The cool thing about the z-table is because we cannot possibly memorize, because you're not always going to have whole numbers like that. You can end up with a z-score that's 2.35. You would probably round up to a one digit, but nevertheless, in order to be very precise as far as what proportion of people fall in that particular z-score, you're going to need to use a z-table which already has all the areas underneath the curve pre-calculated for you. You just need to know how to read it. So in this particular case, if we bring here the normal curve, you have a z-score of -2. So you can see almost less than 3% of the people would be less than that, and almost 97% of the people are above that height. Okay, so by being 50 inches tall, comparing with the mean, which is 60, that means you're extremely short. You would fall within the 3%, minority. Now, let's use this course to compare one person on different measurement units. So we have student A, and we have his scores on different classes. So he took math, English, and science. So he got 33 on math, he got 33 in English, and he got 126 on science. The mean on those classes was 25, 25, and 140, and this is the standard deviation for each particular class. So if we want to compare to see in which class he did best, we can solve every single z-score, one for math, one for English, and one for science, and then we will be able to compare to see how many standard deviations above or below the mean he is simply by looking at the z-score, right? So as we can see in math, the z-score would be 0.8, in English would be 0.4, and in science would be a negative 1.40. So apparently he did best in math, right? Determining proportions. Okay, so by solving for a z-score, you can determine the proportion underneath the normal curve, okay, simply by using the z-score. So right here, right, you having the 60th percentile, which would be all the way up to here, from here all the way to here. And 70 is what? What percentile would be 70? If it's 70 with a z-score of 0, that means this is your mean, this is your average, so this is going to be your 50th percentile. All right, so what is the proportion of people who are under the entire curve? So this whole thing is what? 100% have a score that is higher than the mean of 0. So this is your mean of 0, dead center. So how many people have a score higher than a z-score equal to 0? 50%, because 50% of the curve would be on the right side, 50% of the curve would be on the negative side. Likewise, right, how many people will have a score lower than the mean, which is a z-score equal to 0? Another 50%. All right, so this is the standard normal distribution table, or the z-table. You're going to find that on the back of your book, depending if you have edition 5 or 4. And mine is on page 368, or you simply can look for Appendix A. The table is exactly the same. Now be aware, if you download any Z tables from the internet, I would not recommend you doing that, simply because there are lots of different Z tables out there. And I'm going to teach you how to actually use the Z table that's on the back of your book. Okay, I'm also going to give you an extra copy of it, and I'm going to upload that on Titanium. So what you're going to see, if you go on the back of your book right now, or if you printed out my Z table, the one that I gave you, you're going to see you're going to have a z-score, and then it's going to say area between the z-score, right, between the mean and the z-score. Okay, so here, if you notice, there are going to be no negative signs anywhere, simply because it assumes that the curve is symmetrical. So whatever falls above the mean would be equal to whatever falls below the mean. You just need to simply put the negative sign. We will go over how to use this, okay? All right, so let's work through an example here, and let's go ahead and use our z-table. So the question is, what proportion of scores in the sample are lower than a z-score of 154? Before I give you the answer, go ahead and look at your z-table. Try to locate a z-score of 1.54. Right next to it is going to give you the area underneath the curve that is between the mean and a score of 1.54. All right, always keep in mind that that z-table that I'm giving you, it has no negative. There are other tables out there that they have negative signs, but you read them differently. That's why I want you to stick with this one here, because I'm not going to teach you how to read the other tables. So now let's solve this. So this is actually out of your book. I found 1.54 right here, and then you go right next to it, and you're going to see that it corresponds to an area of 43.82%. Again, so this is the area between the mean and the z-score. This is your mean and the z-score. But the question was to find the area that is less than 1.54. So less would be anything from 1.54 all the way to the very beginning of the curve. So that means that since our table gives us only the area from here to that particular z-score, that we still need to add the 50%, which is the area that is the other half of the distribution, right? So it would be 43.82 plus 50% equals to 93.82%, right, fall below 1.54 z-scores. Now, how about if we have to calculate an area between two z-scores? You're going to see in your homework that I'm going to give you, that is due next week, I'm going to give you different scenarios. Find the area between two z-scores, find the area above a certain z-score, or find the area below a certain score. And depending where you are on the curve, if you're in the positive side or in the negative side, you might need to add or subtract. So that's eventually going to become second nature. You're not going to have to think about it. But let's see a few examples here. So let's just say we want to know the percentage of scores that fall between a z-score of 0.56. Again, this is a positive z-score, right? And a z-score of 1.89. What I want you to be careful here is that 0.56 does not fall exactly on the mean. It's a little bit above the mean. So I'm asking you to find the area that is 0.56 z-scores above the mean and a z-score of 1.89. Okay, so here apparently you're gonna need to look on your z-table, and you're gonna see that 0.56 z-score corresponds to an area of 20.88, and a z-score of 1.89 corresponds to an area of 47.06. Now, what you need to be careful here is to get rid of the overlap, right? Because remember that the z-table gives you from the mean all the way to that particular z-score. But here we're double counting, right? Because you're already having that amount from 0 to 0.56 counted twice, right? Because you're getting it from here and you're getting it from here as well. But you only want from 0.56 to 1.89. That means you need to take this area here and subtract this area here, and you're going to be left with 26.18. And this is what I'm talking about. So you got the two different z-scores, right? So the first one from 0 to 0.56 z-score was 20%. From 0 to 1.89 was 47.6%. And I simply want this area right here, right? I don't want this area. So in order for me to calculate this area, I need to take the z-score from here to here and subtract the area from here to here. And what I'm going to be left with is this area right here. Likewise, another problem, breast cancer survivor dataset. We have a mean age of 56, a standard deviation of 13. What proportion of women would be 69 or older, or 69 or younger? I want you to solve all those on your own, okay? All you have to do is take the Z formula, right? So x minus mu over sigma, and you're going to be taking 69 minus 56, because that's your mu right here, divided by 13. You're going to be finding a z-score. In this particular case, I can tell it's going to be a positive z-score, and you want to find 69 or older, right? So whatever z-score you're finding it, you're probably going to have to subtract it from 50. 69 or younger, so this is going to be the same z-score or that you're going to get from here, only this time you're going to be looking at the opposite direction of the curve, right? And this is in between scores, 56 and 69. Notice that 56 is the same as your mean, so you know that this is a z-score of 0, so I wouldn't calculate this. You simply need the 69, which you already solved, so pretty much the area between 0 and 69. This falls a little bit below the mean, right? So here you're going to be adding, so you're going to be solving for 43, finding that area. You're going to be solving for 69, which you already did, and taking the two areas and adding them. All right, so I know it seems like a lot, but I promise you, the more you practice, I'm gonna also try to post a few other examples, and then midweek I'm gonna post the key to it. So I'm not gonna give you the key right away. I'm gonna post a few exercises for you guys to practice, and then midweek I'm gonna make the key available. This way to you can check your work to make sure that you did it right. But the more you practice, it's just gonna become second nature, okay? You're not gonna have to think if you need to add. In summary, the normal distribution is extremely important, and clinicians use it on a daily basis, because that is the only way that we know that we can identify where an individual falls underneath the curve. We can identify outliers. We can identify where the majority of people fall under. It is always going to be bell-shaped, and it is greatly affected by the standard deviation. Remember that the standard deviation affects the height or the width of the bell-shape distribution. And by simply knowing the z-score, we can identify the proportion of people that fall between above a certain z-score or below a certain z-score, or between two z-scores. Z-scores, again, are standardized scores. And this is it. Okay, you have a good one. And next week, we are going to cover SPSS, and I'm also going to introduce you to your final project. Have a good one. Bye bye.